All right, so I'm going to discuss the notion of a momentum map, which is going to turn out to be a conserved quantity associated with a symmetry of a mechanical system. And for ease of exposition, I'm not going to present the most general formulation of momentum maps, but I'll specify to the case where we're just dealing with cotangent bundles, okay? And that's relevant for Hamiltonian systems. So momentum maps. So let me try to motivate for you it's like the construction. So say you're given a Lie group G, and it acts on a configuration manifold. Which we call Q. Okay. Then the claim is that there is an associated momentum map. Okay, let's call that J. And it's a map from the cotangent bundle, T star Q, which is where positions and momenta live, to the dual of the Lie algebra. Okay, so where sort of the Lie algebra is just the tangent space at the identity of the group. Okay, this is the Lie algebra of G. Okay, all right. So what's going to happen is that we're going to think about this group action, and we're going to look at this notion of an infinitesimal generator, which more or less is a vector field which is defined. It's on, it's like on the manifold, which is going to generate the orbits, it's like of the group action. Okay, so the idea is as follows. Is that if you're given some element of the Lie algebra, which I denote by a C, all right, then there is this idea of an infinitesimal generator. Okay, and that's denoted as CQ. And this is an element of the space of vector fields on Q, okay, which is defined as follows. Okay, so what you do, okay, so because CQ at the point Q is a vector field. It's like, well, it's just a vector, right, when you evaluate at Q. But in general, because CQ is a vector field that's like on Q, all right? And where you get it from is you look at the point Q, and then you have some group element acting on it, okay? But it's going to be a parametrized element of the group. And the way I do this is I take the exponential, the Lie group exponential of, some parameter epsilon times the Lie algebra element. Okay, and so the exponential of this thing is a group element. The group element can act on the point Q. This gives me, again, another point that's like on the manifold big Q. And then I can take the derivative of this respect to epsilon and evaluate at epsilon equals to 0. Okay, so the basic idea, if you will, is that if you have a manifold, you have a point Q, right, then there is a curve which goes through this, which is parameterized by epsilon, which is given by the exponential of epsilon times cos c acting on Q. Okay, and when epsilon equals to 0, of course, you just get Q itself. And so what happens then is that this curve, if you look at the equivalence class of that curve, it's like that's going to correspond to a vector which is based at the point Q, all right? And so this is going to give me, it's like a way of describing or sort of inducing a vector field from the Lie group action on the configuration space. Okay, so that's just in the case of the group G acting on Q, and of course we talked about the idea of cotangent lifts of maps. It's again, so you can cotangent lift this group action as well. Okay, so the point is that you know, the cotangent lifted action of the group, right, is symplectic. Okay, and so what that means is that there exists a local Hamiltonian, locally defined Hamiltonian, let's call that J sub C, which is a map from the cotangent bundle to the rails. All right, so such that the infinitesimal generator associated with the cotangent lifted action, so I denote this by C T star Q, right? And this is now going to be on T star Q, so I have an element T star Q which I denote by alpha Q. So this whole thing is an element of vector fields on T star Q, if you will. All right, which is of course where the Hamiltonian vector fields live, right? And this is equal to, the claim is that this is equal to the Hamiltonian vector field associated with J sub C, and then evaluated at the point alpha Q. Okay, so let's try to recap what's happening here. So what's happening is that you have a group G acting on a configuration manifold Q. You can tangent lift the group action, okay? And the point is that this tangent lifted group action is going to be symplectic, so you can locally express it as the flow, if you will. It's like respect to a Hamiltonian vector field, which I'm going to call J sub C. All right, and it has the property then that the infinitesimal generator of this cotangent lifted action is equal to the Hamiltonian vector field associated with this local Hamiltonian J sub C. Okay, so now it's like one has to make a few assumptions, and what oftentimes happens is that this J C, you can ask, well, how does it depend on the algebra element? And oftentimes it depends linearly on the algebra element. And if that's the case, so if J C depends sort of linearly on this C element, then we can introduce the idea of a momentum map. A momentum map. Okay, J, which is a map from the cotangent bundle to the dual of the Lie algebra. Okay, and the way you define this, of course, is that, so what does that mean? So you have a J, and you have to evaluate it on a point on the cotangent bundle, which I denote by alpha Q. So this thing now is an element of the dual of the Lie algebra, right? Which means that it's a linear functional which acts on Lie algebra elements. So I'm going to pair it with a Lie algebra element, okay, and there's a natural pairing, and I should give you what the scalar value thing is. Okay, and what you want it to be really is that you want this J to somehow encode all of these J sub C local Hamiltonians, which generate the sort of the Hamiltonian vector field, which encodes again this infinitesimal generator associated with each of these algebra elements. So, so what you want is that you have J C, right? J C is just a scalar value function on T star Q. So you're just J C acting or evaluated at alpha Q. So this is the definition, if you will, of what is called the momentum map, and it's a very nice setting because, amongst other things, it allows you to generalize notions like linear momentum, angular momentum, and so on. And it sort of it gives you a very systematic framework for studying conserved quantities associated with symmetries of Hamiltonian systems. So again, it's like the theory is somehow a little bit more general. It's like it doesn't just apply, of course, to cotangent bundles. It applies more generally to Poisson manifolds. But for the purposes of this class, I think it suffices to look at this more concrete case. So let me just stop here for now.